Lab number 5 is our second in a series of OSPF videos. Specifically, lab number 5 focuses on multiple areas and frame relay non-broadcast. To begin with, we're going to see the characteristics of a non-broadcast OSPF network type. We're going to discuss the characteristics of multi-area OSPF networks. Then, we're going to take a look at the concept of a virtual link. We might need a virtual link if we have one network area that is not directly adjacent to the backbone area, to area 0. Then, we'll take a look at the syntax for OSPF configuration, and we'll set up OSPF for multiple areas. Next, we'll configure OSPF for the non-broadcast OSPF network type, and we'll set up one of those virtual links. Finally, we will verify our configuration.
In this lab, we want to illustrate a characteristic of the non-broadcast OSPF network type. The non-broadcast OSPF network type is the default, by the way, on frame relay serial interfaces. And with this network type, unlike in the previous lab, where OSPF neighbors dynamically learn about one another, with a non-broadcast OSPF network type, the OSPF peers do not dynamically learn about one another. In fact, we're going to have to go in and use a separate statement. We'll have to use a neighbor statement to educate these routers about one another. And something else to be aware of in this non-broadcast OSPF network type, all of the routers are part of the same subnet. That's different than in previous labs. I'll show you the topology in a few moments, and we'll see how these routers actually are on the same subnet. And unlike the point-to-point OSPF network type that we saw back in lab number 4, here with a non-broadcast OSPF network, there is a designated router that is elected. And we're also going to have multiple OSPF areas in this lab. If you remember, in lab number 4, we discussed a big benefit for having multiple areas. We could constrain the flooding of link state advertisements, LSAs, to within an area. So if there's a network change, that change does not have to be propagated everywhere throughout the entire OSPF topology. That flooding could be constrained in an area, and then, as we'll talk about in the next lab, we could send summary information, if need be, from one area to another area. So this is going to reduce the flooding of route changes throughout the topology. And when we do have multiple areas, one area serves as the backbone area, and that backbone area must be numbered as area 0. Another restriction that we're going to illustrate in this lab is that every other area, it must be physically adjacent to area 0. In other words, if I had a router and one of its interfaces belonged to area 0 and another interface belonged to area 1, that would be fine because area 0 was present on that router. Or if another router had all of its interfaces in area 1, that would be fine because there would be an area border router, an ABR, that connected area 1 back to area 0. However, what we're going to see in this lab is that we have a discontiguous area. We have an area that has no direct linkage back to area 0, and that is going to cause us an issue. We will illustrate, however, how to overcome that issue using a virtual link. A virtual link can be used when we have an area that is not physically adjacent to area 0. What we can do is go into an area border router for area 0 and an area border router for that discontiguous area, and we can form a virtual link between those two routers. We'll take a look at how to do that in this lab. But for now, let's check out the topology we're going to be working with. A few things have changed in our topology since last time. For example, in lab at number 4, all interfaces for all routers belonged to area 0. We only had a single area. Now you'll notice we have 3 different areas. Area 0, Area 1, and Area 2. And it looks like we're violating an OSPF design rule, doesn't it? Area 2 does not appear to be adjacent to Area 0. That can cause us an issue. We'll overcome this discontinuity using a virtual link in this lab. That's going to make router R2 appear to be adjacent to area 0. Something else that has changed since the previous lab is that now routers R1, BB1, and BB2, they're now part of a non-broadcast frame relay network. Specifically, instead of using sub-interfaces as we did previously, now router R1 is connected into the frame relay cloud via its serial 0/0 interface, the physical interface rather than the sub-interfaces. And the same goes for routers BB1 and BB2. We have a couple of PVCs, permanent virtual circuits, built on these physical interfaces. Those are still in place, but you'll notice with this non-broadcast configuration, all of the routers connect into this frame relay cloud as members of the same subnet. Everybody is a member of the 172.16.1.0/24 IP address space. Previously, we had one network between R1 and BB1, and another network between R1 and BB2, and a third network between BB1 and BB2. Now all of these routers have their serial 0/0 interfaces as a member of the same subnet. And something we're going to notice about this non-broadcast OSPF network type, the neighbors are not going to be dynamically learned. So we will need, for example, to go into router R1 and educate router R1 about routers BB1 and BB2. And we only have to educate one end of a PVC, by the way. We don't have to have a configuration on both routers at each end of the PVC. But after we educate router R1 about its neighbors, we still have a PVC over between BB1 and BB2. So we'll go over to one of those routers and we will enter another neighbor statement to make sure that BB1 and BB2 know about one another. In fact, let's take a look right now at the syntax that we're going to be using. Some of the syntax that we'll use in this lab is the same syntax that we used back in lab number 4. For example, we will still go into the router configuration mode by saying router OSPF and giving a locally significant process ID. We will still educate the OSPF routing process about the networks we want to advertise in a particular area with the network command as we see on screen. A command that we did not see last time in router configuration mode is the neighbor command. We say neighbor and we follow the neighbor statement with an IP address, the IP address on the other side of a permanent virtual circuit. For example, from the perspective of R1 based on the topology we just saw, we would say neighbor 172.16.1.2 to point router R1 to the backbone router of BB1. That's BB1's serial 0/0 interface. Once we did that, then BB1 and R1, they could establish an OSPF adjacency between themselves. We're also going to have an issue with an area that is not attached to area 0, and that's going to be area 2. We're going to fix this discontinuity with a virtual link. The way we're going to create a virtual link is by going into routers R1 and R2 and entering the command you see on screen, area followed by a number. That number, by the way, that's the number of the area that we have to transit to get between the backbone area and this discontiguous area. In our example, that transit area is going to be area 1, so we will say area 1 virtual-link followed by the router ID of the router at the far side of this virtual link. So on router R2 we will give the router ID of R1, and on router R1 we will give the router ID of R2. That's the theory and the syntax. Let's now go out and walk through the configuration